So I posted the key to the exam. If you've got particular questions about why I took points off in certain places, please check the key, come talk to me. Some of you have notes on your exam asking you to come talk to me. My goal is to figure out how to let your grades get to where you want them from here. All in all, I was not unhappy with the exam, and this was a very calculation light exam. We will see more formulas like from all of these probability discussions that we're having. This is when I start saying, okay, now it makes more sense for you guys to get a formula sheet and calculators, or as you saw, I gave you a bunch of stuff. Here's the calculations. Tell me what things mean. In one sense, that's part of the more difficult side of it. Calculations I can do on the computer. The calculations I can do on my calculator. The interpretation has to happen in your head. Speaking of, I want to go back to our probability ideas and continue there. We had, the end of class Wednesday, this discussion of breakdowns of student engagement versus status within an MBA program. So I've got students with low engagement, medium engagement, high engagement. I've got students in the full-time program, the part-time program, and the executive program. And then on the ends of each row and at the bottom of each column, I have totals. So the best part about this is calculating probability from here is really easy, provided we know what kind of probability we are looking for. So this table appears on page 170. But let's consider, if I ask you to pick a random student from the MBA program, what is the probability that that student is in the executive program? Well, now I need the total against the total. Well, the total what? The total in the executive program, max? Out of? Right, my whole group. But if I asked how many of those students have medium engagement, then what I'm asking is a conditional probability. The probability that a student has medium engagement given that they are in the executive program. In which case I've been restricted to only working within the row for the executive program. So what is that probability? Exactly. Since I'm only looking at this row, given that I am an executive program, means I can basically ignore the rest of the table. But an and statement. Now, there are two different ways to calculate this. One is to use the conditional probability formula, right? But another is to say this is a joint probability, and really then is comparing one cell of this table with the overarching total. So in that case, what is this probability? Exactly. But notice that's the same result as if I said, oh, well, I'm going to take the conditional probability and multiply by the original probability of just being in that executive. And this is 16 over 37 times 37 over 360. And the 37s cancel, giving me the 16 over 360 that we got the other way. You are welcome to take all of those numbers, turn them into decimals or percentages. That's not the important part of this. The important part is pulling where these come from. I'm going to keep working with this table. What was my definition for independence? Go back and look. We wrote it down Wednesday. No?
A equals A out of B.
Probability, not percent, and A given B. But yes, right? So if my conditional and my joint, wait a minute, my conditional probability was measured right there. Okay, so I don't have the other P of A. If my two events are in the medium engagement given the executive, what do I need to compare that to? If I want to know if medium engagement and executive program are independent, what do I need to compare this number to?
The executive given medium engagement.
Why?
Because in that way you're comparing it against like it's not given some other
Okay. If I were trying to compare it with this one, yes. If this is the executive, then the executive needs to go in this side, right? But I already have medium in this side, so I could do another comparison. I could say, in order to determine if medium engagement is independent of executive program, I could compare these two, right? A given B and A. Or I could reverse the order and I could say the comparison of medium given executive with probability of just being in the medium engagement class. So in either case, I'm going to need one other probability to compare it to. If I'm using this version, then I'm comparing the 37 over 360 with a number I don't have yet. If I'm using this version, I'm comparing the 16 over 37 with a number I don't have yet. In either case, I need one more probability. So Mike, which one do you want to do? The top one or the bottom one?
Oh.
Okay, so I know that this number is 37 out of 360. How do I find this number? I go back to my table. This is the probability of being in the executive MBA program, given that you are a student of medium engagement. My students of medium engagement are in the middle column. And the executive MBA group is this number. So what is the probability of executive given medium?
16 out of 52.
Are those two numbers equal? Grab your calculators. Because the number on the left is 0.10, the number on the right is 0.30. Sorry, the other way around. The number on the right is 0.10, and the number on the left is 0.30. Those are definitely not equal. If they're not equal, these are not independent. Check the other ones. What I didn't get already, I mean, I have this number. This number is 16 out of 37. That's up here. What's this number? Grab the table. What's the chance of being in the medium engagement group? Out of? Exactly. Medium engagement group's this whole column. So I take the column against the end. And 53 out of 360 is not the same as 16 out of 37. 0.4, 0.15. Definitely different. Questions? Sometimes the table will get rewritten so that everything in the table itself is already a probability. The following is the same table. Okay. But all I did is I took every number and divided by 360. Now watch what happens in my row totals and my column totals. Everything adds up to 1. So now instead of actually having to do the divisions necessarily, when I'm dealing with single probabilities with the joints, the ands, it's easier to do this way. There is the possibility of some round off error. So we could get things that don't precisely add up to 1 all the way across the bottom or all the way down the side, given the way we round in the interim here. A recycling hole. On a number of soda bottles, particularly glass bottles, you'll see a deposit. Hey, if you bring this bottle back to a bottling recycler, we'll give you a nickel, a dime per bottle. if you live in a state with a deposit law, they surveyed 1,000 people and asked, hey, do you live in a state with a deposit law? Yes or no? Do you recycle your glass bottle? Yes or no? And out of the 1,000 people, this is what we saw. What's the chance that somebody recycles? Out of? So that's 34%, right? 0.34. 34 out of 1,000. Great. What's the chance that they don't recycle, given that they live in a state with a bottling deposit? Aha. Living in the state with the bottling deposit, 66 out of 220 don't recycle. So grab your calculator. What's 66 over 220? What do you got? 0.3. So there's only a 30% chance somebody who lives in a state with a recycling law or deposit law doesn't recycle their bottles. Okay. What's chance you live in a recycling state and, sorry, you live in a state with a deposit law and you recycle? Ooh, I said the word and. If I'm doing and, then I'm not comparing this with the column total, because that would be given that you live in the deposit law, right? I said, what's the chance you recycle and you live in a state with a deposit law? That's this number compared directly to the total overall. Absolutely. If I do 154 over 220, that's the chance you recycle given that you live in a state. We restricted ourselves to this column, right? So I'm only looking at states that have a bottling law. Sorry, my hand is too bright. So if I say you're only allowed to look at states with deposit laws, that's the conditional probability. That's given you live in a state with a bottling law. But I said, what's the chance you recycle and live in a state with a bottling law? So now I'm looking at everybody, all 1,000 people. You live in a state with a recycling law, and at the same time, do you recycle? So I'm looking at the whole total, but I'm looking at the overlap of those two. I'm still looking at the 154 people, but it's out of the total population rather than out of just the subpopulation that recycles. That's right, that lives in a state with a deposit law. Better? So I can ask the question right now, is recycling independent of law? The chance of recycling given state law would be 154 out of 220. The chance of recycling total is 34 out of 340 out of 1,000. What's 154 over 220? What was that percentage? We never calculated that one. 70, because the other one was 30, right? The chance of not recycling was 30%. So the chance of recycling must be 70%. 70% versus 34%, those are not independent. The probabilities aren't the same. Knowing that someone lives in a state with a bottling law, with a deposit law, changes whether or not you think they will recycle. Questions? It's kind of weird. Sorry, another way to think of this is to think of the decisions and the questions we're asking in the order we're asking them. So another approach to this is something called a tree diagram. So let's consider another contingency table. So we're going to look at a contingency table about risk analysis, expense ratios, and bond funds versus stock funds. So I have funds, I have bonds and stocks, and I have the expense ratio. Is this a low expense, a medium expense, or a high expense fund? And we surveyed 44 funds. There are 44 total in here. Out of the bond funds, there were 21 bond funds. 3 were high, 7 were medium, and 11 were low. There were 23 stock funds. 11 were high, 9 were medium, 3 were low. That gives me a 14 total here, a 16 total here, and a 14 total there. So this is my contingency. So now, I want to think about grouping these and making the question, we can ask the question in 2 different ways. We're going to end up with 2 possible tree diagrams. Which do you want to consider first? The type of fund or the expense ratio? We're eventually going to do it both ways, but I want you to decide which way we're going to do it now. Okay, so that means I'm thinking about the rows. And when I do the rows, I'm going to say, okay, I can either go low, medium, or high. Those are my choices, right? Now, these numbers right here tell me low, medium, and high, right? So I could say there's a chance when I make this decision, there's a chance I'm on the top branch, a chance I'm in the middle, and a chance I'm on the bottom. What is the chance that I am on the top branch? That the thing I picked is a low expense item. Oh, well, there are 14 low expense items out of a total of 44. That's the chance of being on that branch. How about the middle branch? I heard it. Out of. Exactly. And the bottom branch would then be high. 14 out of 44 again. Now notice, if you add up those fractions, you get 1. Because when you pick something, it's got to have an expense ratio. But now each of these can be subdivided. And these branches are now conditional probabilities. Sorry, I'm looking within each row. Because if I'm up here, I know I'm restricted to this first row. If I'm in this first branch, I must be in this first row. So the probabilities have to go with these numbers. So this top number here, what's the chance I end up here? That's 11 out of 14. And the chance I'm on the bottom is 3 out of 14. And notice those two branches, since they descend from the same root, larger branch, I'm not sure what I want to call that. Those two add up to 1. 11 over 14 plus 3 over 14 is 14 over 14. That's a 1. What would go here in this middle set of branches? Talk to me. We're on the medium. Aha. That's okay. There. 7 out of 16 and 9 out of 16. Now the 3 and the 11 here go with the high expense ratio. That's going to go here. 3 out of 14 and 11 out of 14. Now notice, I haven't actually written down what these probabilities are yet. But let's go back and talk, because I said them verbally, I didn't write them down. This number right here, this 14 out of 44, is the chance of a low expense ratio. This number here, this 11 out of 14, this is the chance you have a bond fund given that you have a low expense ratio. Because you're restricted to that first branch already. This down here, that's the chance you have a stock fund given you have a low expense ratio. Remember that conditional probability formula we mentioned earlier? If I take these and I multiply them together, the chance of a low expense ratio and a bond fund is the chance bond given low multiplied by the chance of low. I'm reading the branches. And so that would be 11 out of 14. That's 14 out of 44, which is 11 out of 44, isn't it? Right? And that's the same, slide back up to the table, as if I took this box against the whole total. You see the difference now, Suri? When I'm measuring against the whole thing versus when I'm measuring against the row. And I can go through and I can write that same calculation for each of these 6 branches. But we made the decision to go expenses first, right? So we have 3 branches to start with, and then each of those has 2. If I made the decision to go with the type of fund first, I could do this a different way. And from each of these, do this. Now, instead of going across the rows for this second part, I'm going to go down the column. So let me start by going back to the table for a second. It's out of 44. What's the chance I have a bond fund? So that number, 21 out of 44, goes here. And the chance I have a stock fund, 23 out of 44. This number, the chance that I am in a low expense ratio, given that I am in the bond pile, because I'm working down the column. And then medium and high. Notice the chance of low and bond is now the chance of low given bond times the chance of bond. But those are still these two numbers, aren't they? Low given bond is 11 out of 21. Bond total is 21 out of 44. And if I multiply, I get 11 out of 44, which is the same thing we got there. It works the same way. If I were to work out all 6 of these, or all 6 of these, those numbers would add up to 1. Up here in this group, these numbers add to 1. These numbers add to 1. When I figure them out, those numbers will add to 1. Back in this table, these numbers add to 1. These numbers add to 1. Add to 1. Add to 1. All the branches with a common root add to 1. Questions? I only made 2 decisions here, right? What type of fund I had, what type of expense ratio I had. I can make decision trees for many more decisions. The more layers of decisions I have, the more complex and more branching my tree gets. The problem with trying to do a table like that is if I have 3 decisions, then I'm really going to need like 3-dimensional tables. I'm going to need a row and a column and a page number. And that's kind of weird, but that's one of the powers of spreadsheets and databases is that I can do exactly that. And it's much easier to do these calculations in something like Excel to build, or even in a database program like FoxPro or DBase or whatever database program you want to use to make this happen. Questions? Mm. 47. Let's look at shopping tendencies of grocery shoppers who have a shopping cart. 70% pay by credit card or debit card, 20% pay cash, and 10% pay by check. Do you know anybody that writes checks anymore? Yeah, it's an archaic skill. Of shoppers without a cart, 50% pay by credit or debit, 40% pay cash, and 10% pay by check. On a Saturday morning, 80% of the shoppers take a cart, 20% don't. What's a tree that I can use to figure out what's going on here? Notice they didn't give me a table, but they gave me all the pieces of information I need to build either a tree or a table. I think it's probably easier to build the tree directly, but we'll do both. So let me start with my root decision from, hey, a person walks into the store. What's the only single piece of information I'm given here? Because up here, all of these numbers say of grocery shoppers who have a shopping cart, of shoppers without a cart. So I need to start with, did they get a cart or not? That's my first decision. With cart, without cart. And I'm given numbers for that, so I can actually fill in the beginning of my tree. They either get a cart or they don't. And we were told the chance of a cart. And the chance of no cart is 20%. Now remember, those have to add up to 1. They were given in percentages. I'm already getting the decimals. I don't have any fractions involved. And then we have 3 payment options. We have credit card, cash, and check. So credit card, cash, and check. And now I can go through and put numbers on these. What's the chance with a cart somebody pays with a credit card? So that's a 0.7. Cash and check is the rest. Notice those add up to 1. Then down here without a cart, it was not. It was 50. And then 40. And then 10. Great. What's my table look like on this? Okay, you have to tell me which way you're going to divide stuff up. Is cart versus no cart row or column? It's literally a coin flip. The table is going to look exactly the same either way. We're just going to have it either across or down. Which way do you want to do it? Down. So cart, no cart. And then we have credit card, cash, or check. And now I can put numbers in here. There was a 0.8 here. And a 0.2 here. But now I have a problem. This 0.7 doesn't actually go in the table. Where's that 0.7 come from? This 0.7 right here. Where's that number come from? So that 0.7 is equal to something over 0.8. It's a conditional probability, which means this up here is the chance of cart and credit card, which we've not computed anywhere up here. I could multiply those together, couldn't I? Oh, 0.7 times 0.8 is what's 7 times 8?
0.56.
56. And that's the number that goes here. That's what happens if you multiply this number and this number on this end. I'm going to do the same thing here. 0.8 times 0.2 is 0.16, and 0.8 times 0.1 is 0.08, and those add up to 0.8. No cart, I do the same thing here. And now I can get some information that I didn't have before. I can get the information. What's the chance a person pays with a credit card? Whether they have a cart or not, that would be the number here, wouldn't it? But now I can get that. That's 0.66. The chance that a person pays with cash is 0.24. The chance that a person pays with a check is 0.10, regardless of whether they have a cart or not. So I was able to work out the other pieces of my probability. And notice that if I total all of these numbers here, all 6 of these numbers together add up to 1. I was able to get information not in evidence by working out this tree diagram and or the corresponding table. Oh, I like it. Questions? Now, the important information out of this is that I got more info than I started with. And that happens more often. And a mathematician by the name of Bayes came up with a new way to figure out conditional probabilities, the same idea. So here is Bayes' theory. And he said, a way to get the conditional probability of B given that A has already happened is to use our definition, which says we can do probability of both divided by the probability of the second. But sometimes we get this from the other, notice this is backwards, the other conditional probability. I can get one conditional probability from the other one. Now, I am the first person to tell you that theorem pisses me off. It's not an intuitive behavior. It really requires me to understand that this A and B works in both directions. I'm multiplying the two numbers together. It doesn't matter what order I multiply them in. So the probability of B and A is the same as the probability of A and B. It's just the way in which we go about finding those numbers. But really, if I had my table and I had all of the pieces labeled on my table, like we did here, what I'm missing are these numbers here on the end, right? So I don't have the chance somebody pays with a credit card automatically sitting in front of me. I can work it out, but I don't know it already. But I have all of these numbers. I have all of these numbers, which are also conditional numbers. So another way to work out Bayes' theorem B given A is chance of A given B times the chance of B over. Now here's the ugly part. The same thing goes on the bottom. And I add the chance of A given not B. Chance of not B. That's really only useful when I don't have probability of A directly, when all I have are conditional probabilities. This is in the textbook. There's an example, page 178, but I think this example sucks. So I'm going to try and redo this example in a slightly different way. So let's read the example the way they wrote it on page 178, so I can figure out what's going on. 10% of the women who purchase an over-the-counter pregnancy testing kit are actually pregnant. For a particular brand of kit, if a woman is pregnant, the test will yield a result positive 96% of the time. And a negative result 4% of the time. That means that a false negative. Somebody comes up, the test says, I'm not pregnant, but they actually are. If she's not pregnant, the test will yield a positive result 5% of the time, a false positive. And a negative result 95% of the time. Woman buys the kit, takes it, test comes up positive. What's the chance she's really pregnant? The problem is the way we were given the probability. We were given the probabilities of women that are pregnant. The test does this. Of women that aren't pregnant, the test does this. But now I'm telling you the test did this. Is she pregnant? Now maybe pregnancy tests aren't your thing. Change every word pregnancy here to flu. You have the flu or not? Same idea, but the problem is the setup. So I'm going to write out a tree for this because I don't like that paragraph of text. Working off this tree, we were told a woman takes a test or she isn't. She's either pregnant or not. And the assumption was out of 1,000 people, 10% of them who buy the test are actually pregnant. So our assumption is that that's 0.1. So what's the probability on the bottom branch? You're either pregnant or you're not. And if you went and bought a test, the assumption is that 10% of the people who buy the test are actually, say again, 0.9. So that's the rest of them, because those have to add up to 1. And then it said, if you are pregnant, the chance you get a positive result is 96%. The chance you get a negative result is what? 4%. If you're not pregnant, the chance you get a positive result, a false positive, is 5%, which means the chance you get a negative result is 95%. Now, let me put symbols to these. This number, 0.1, that is the chance that a person is pregnant. The 0.9 is the chance that a person is not pregnant. What is this 0.96? Based off my branches, that's the chance that I got a positive test result given the person was pregnant. And the 0.04 is the chance I got a negative test result given that the person was pregnant. The 0.05 the person isn't pregnant, given that they're not pregnant, I still got a positive test result. And the 95% they're not pregnant, I got a negative result. But what I want is what is the chance that my person is pregnant given a positive result? None of this information directly gives me that number. I have to reverse these conditionals, don't I? That's when I need Bayes. Now, I could use this if I had the chance of a positive, but I don't have chance of positive alone. So I'm going to have to use this bottom version. And that is the first calculation we will do on Wednesday. So I will see you all then. I hope you have a wonderful rest of your day. And if you have questions about your exam, come talk to me.